Then comes quantum, which then does not allow you to predict things with a lot of certainty or things with unlimited certainty. There is a uncertainty principle that limits your puts a limit on your observations as far as the certainty, such as, so you cannot know both the position and the velocity of a particle with complete accuracy. There is a limit to the certainty there. Quantum mechanics deals with this situation via a class of quantum theories in which particles don't have well-defined positions and velocities but are represented by a wave. These quantum theories are deterministic in the sense that they give laws for the evolution of the wave with time. Thus, if one knows the wave at one time, one can calculate it at any other time. Thus, if one knows the wave at one time, one can calculate it at any other time. The unpredictable random element comes in only when we try to interpret the wave in terms of the positions and velocities of particles, but maybe that is our mistake. Maybe there are no particle positions and velocities, but only waves. It is just that we try to fit the waves to our preconceived ideas of positions and velocities. The resulting mismatch is the cause of the apparent unpredictability. Hello, everybody, once again. In effect, we have redefined the task of science to be the discovery of laws that will enable us to predict events up to the limits set by the uncertainty principle. The question remains, however, how or why were the laws and the initial state of the universe chosen? In this book, I've given special prominence to the laws that govern gravity, because it is gravity that shapes the large-scale structure of the universe, even though it is the weakest of the four categories of forces. So isn't that so crazy that gravity is the one which is so universal? Everything is affected by gravity, but it's also the weakest of the four categories of forces, and very hard to unify it with the other three types. We talked about that a lot yesterday. So, okay, the laws of gravity were incompatible with the view held until quite recently that the universe is unchanging in time. The fact that gravity is always attractive implies that the universe must be either expanding or contracting. According to the general theory of relativity, there must have been a state of infinite density in the past, the Big Bang, which would have been an effective beginning of time. Similarly, if the whole universe recollapsed, there must be another state of infinite density in the future, the Big Crunch, which would be an end of time. Even if the whole universe did not recollapse, there would be singularities in any localized regions that collapsed to form black holes. These singularities would be an end of time for anyone who fell into the black hole. At the Big Bang and other singularities, all the laws would have broken down. So God would still have had complete freedom to choose what happened and how the universe began. When we combine quantum mechanics with general relativity, there seems to be a new possibility that did not arise before, that space and time together might form a finite four-dimensional space without singularities or boundaries, like the surface of the Earth, but with more dimensions. So we must thank Stephen Hawking for combining quantum and classical, especially with the black hole, and giving us temperatures of black holes. It seems that this idea could explain many of the observed features of the universe, such as its large-scale uniformity and also the smaller-scale departures from homogeneity, like galaxies, stars, and even